Next, now we are going to consider I section, but weak exit bending. Okay, so in the previous one is I section, but strong exit bending. But now we consider the weak exit bending like this. So first of all, we have to think about where is P and A. There are two possibilities. The first possibility is the PNA in web. Okay, and the second, and okay, and this one, if PNA in web, then the ratio between MPC and MP can be determined by using this equation in the textbook, equation 2, 5, and 12 in your textbook, like this. Okay, so you can check in textbook or you can use this one. It's okay. In case PNA is in flank like this, PNA, then the ratio between MPC over MP can be determined by using this equation, equation 2, 5, and 13, like this. And you can check also in the textbook, in your textbook, this equation. Okay, so you can check in detail in the book. Okay, but the procedure, I already talked about the procedure in the previous example. So for the save time, we don't talk very detailed. And for practical design of I section with quick exit bending, it is said that if the middle web, okay, does not contribute, if this is too small. Small means the P over Py is smaller than 0.4. Then this portion does not contribute to the moment resistance. Okay, moment area is too small. Then the web is not have a significant contribution on the moment resistance, so it is ignored. It is neglected. It means when P over Py is smaller than 0.4, then we use this equation MPC equal to MP. We assume MPC equal to MP. Okay. But if this ratio is greater than 0.4 and of course is smaller than 1.1, then the approximation equation MPC equal to this is used. Okay, it's used. So the two equation is used for practical design of the I section in case weak exit bending. So remember this approximate equation. Okay, so different curve corresponding to different ratio between AF over AW. AF means the section of the flank, and AW means the section of the web. And different ratio has a different curve, and if the ratio equal to 0 means rectangular, then we have lowest curve. But for convenience of design, and we use approximate equation. Okay, so next is effect of shear force on MP. Previous one we consider effect of the action force, and now we consider the effect of shear force on MP. First, we consider the rectangular section. As you know, in shear force, we use the von Mises yielding condition. Have you ever heard about von Mises yielding condition? I believe you already learned about von Mises yielding condition, right? For shear force, it is this equation. Okay, it is von Mises yielding condition. In the elastic phase, you already know. In elastic phase, MPS equal to 1 over 6 of sigma y p d square. And shear force in rectangular equal to this equation. Okay. Here, tau y equal to sigma y over square root of 3. For elastic plastic phase, we have MPS equal to MP multiplied by this equation. Okay, this equation is depends on y0. Depend on y0. And the shear force now in the elastic plastic phase, it is assumed that in fully plastic, no shear resistance anymore. So shear equal to 4 over 3 of tau y b y0 tau y. For y flank section, in y flank section, this is actual stress diagram, shear stress diagram. It is actual shear stress diagram. Okay, it is not a rectangular shape, but it is the nonlinear curve. So for convenient calculation, a simplified shape is used. In simplified shape, tau equal to V divided by AW. V is given. V means shear force, the given shear force. And AW is the area of the wave, section area of the wave. Okay. And this is shear, and this is moment. This is normal stress in a section. For the flank, the stress is sigma y. For the wave, stress is equal to this equation due to von Mises condition, right? The von Mises condition. So sigma in the wave is equal to this equation, and because of shear force, sigma in the wave smaller than sigma y. Then MPS smaller than MP. Now we are going to calculate MPS. MPS equal to MF plus MWS. What is MF? MF is due to the flank. Okay, so moment due to flank. And MWS is the moment due to the wave. In this case, it is the effect of the shear. Okay, and we can divide that is mf and mws, and here is mw. Mw means the moment in case without the effect of shear. Okay, moment of the wave in case without of shear. Then now we have mps equal to this one plus this one is mp. Okay, mp. In this case, no shear force is considered. Okay, then this part can be rewritten to be this, and because mws equal to sigma multiplied by zw, and mw equal to sigma y multiplied by zw, then we replace this one to here, then we have this equation mps equal to mp minus mw multiplied by 1 minus sigma over sigma y. Then ps, gps, the reduced plastic section modulus equal to the original plastic section modulus minus the section modulus of the wave only, plastic section modulus of the wave only multiplied by this. It is the function of sigma over sigma y, and sigma can be calculated by using this equation as a function of sigma y and tau. And tau is v over aw. Okay, so we can calculate. If we have a section and we have shear force, then we can calculate ZPS. For example, let's consider the I section here. The I section is this one. Okay, and with this one we have Z equal to 139. It is plastic section modulus of the whole section, and we use a 36 steel. It means sigma y equal to 36, and it is a section of the thickness of the wave and the height of the wave equal to this one. Then you can calculate AW, right? And the shear force is V equal to 100 kV. Okay, it is shear force. So please calculate MPS. What is MPS of this section? For MPF equal to ZPS multiplied by sigma y. So if you can determine ZPS, then we can calculate MPS. And we already know how to calculate ZPS using the previous equation, right? Okay. ZPS equal to Z minus ZW and multiply this ratio. And we already have this one here. And what is this one? It's a function of this one and this one, right? Calculate. Because we have tau equal to V divided by this one of the wave, V divided by A wave, and equal to 100 divided by this one multiplied by this one, and equal to this one. And tau y equal to sigma y over square root of 3 and equal to this one. And we found that tau is smaller than tau y. And sigma equal to this one. It is von Mises equation, or equal to this one. We have sigma y and we have tau here, and we can calculate sigma. And this one is a function of here tw and dw. And finally we have gw equal to this one. Now we have all. Sigma y, we have sigma and g and gw. Then we can calculate ps. GPS equal to this one. Okay. Now compare GPS with G. Then GPS and G. We found that the reduction is very small, just 5%. Okay, just 5%. What does it mean? So because of the reduction is very small, then in LRFD, if tau smaller than tau y, okay, tau smaller than tau y, then shear stress can be neglected. Okay, it means in LRFD design, if tau smaller than tau y, we have tau y here, and you can calculate tau using this equation. And if it is smaller than tau y, then we can neglect the shear stress effect and just use G. Okay, original plastic section modulus. Okay, now I'm going to show you one more example on how to determine the shape factor of arbitrary section like this. So let's say here is T section. T section. We have all dimension here. Okay, all dimension with T section. And be careful here on the tension. Sigma tension equal to 1.5 sigma y. Not sigma y, but 1.5 sigma y. And in the tension, sigma T equal to sigma y. Okay, so it means in compression, the yielding strength is 1.5 sigma y, and in tension, yielding strength is sigma y. And we have section, we have a yielding strength of different area. Let's say in compression and tension. So we have to calculate shape factor. Shape factor means F equal to, shape factor means F equal to MP over My. It is a shape factor. Shape factor, okay? And we have to calculate MP and My. So how to calculate MP? The tension is in wave. So we have elastic section modulus equal to opposite section equal to 4.61. Okay, and what is MP and what is F? To determine MP, we have to determine PNA. So in this case, because in compression and tension is different, so we cannot use this one, but we use this one. F1 should be equal to F2. Okay, because in compression and tension, the yielding strength is different. So F1 equal to F2. We assume P and A is in the flat. So we have to determine YC. So let's say this part, okay, this part is F1 in compression, and the rest one is F2 in tension. F1 should be equal to F2. What is F1? F1 equal to 6 multiplied by YC multiplied by 1.5 per sigma Y. And what is F2? F2 can be divided into two parts, wave and flank. This is F2 in the wave, in the flank, in the wave, and it is F2 in the flank. Okay, then only one unknown. Here is YC, then we can calculate YC equal to this one. And from the, if we have YC, and now we can calculate MP. MP equal to this one. You can check. Okay, here MP equal to this, the force here. Okay, let's say F1 multiplied by a distance between this one and for example here's F2. Then this is the distance D. Okay, the distance D. Okay, you can divide by different part. Finally, you can calculate MP equal to this one. Very simple. You can divide different way and then calculate this. And finally, we have F equal to MP over My. F equal to MP over My. You already know My equal to sigma Y multiplied by S. Okay, My equal to S multiplied by sigma Y is here, and this is MP. Then the ratio is 1.86. So the solution of the shape factor in this section, T section, with this different dimension, F equal to 1.86. That is final solution. Okay, now it's homework number 3. I will give you one homework problems. Problem P 2.9 in textbook, not copy from each other. Okay, good luck. See you next week class.